Hello everyone, my name is Ajay Merdi. In this presentation, I am going to discuss about a simplified virtual abstract avoidance approach for aircraft altitude bounded flight maneuvers. Abstract. Avoiding collision with obstacle and terrain has always been a critical issue for aircraft during low altitude flight landing and approach maneuvers, especially near airports located in mountainous areas. In low altitude flight, it is desirable to find a safe trajectory that is compatible with the aircraft capabilities and at the same time optimizes flight efficiencies. Safety is a fundamental concern when in terrain following TF and or terrain avoidance flight modes and aircraft designed for these types of missions emphasizes the inclusion of terrain and obstacle avoidance flight capabilities. Introduction. Safety related requirements as well as a desire to increase the efficiency of air travels have led to the use of required navigation performance equipment and procedures and required navigation system. One of the aircraft equipment requirements according to RNAV is a terrain awareness and warning system. The goal of TAWS is to provide protection against flight into terrain and obstacles and minimize the nuisance warnings. Therefore, aircraft flight near the ground requires the definition of a low altitude flight mode in the onboard autopilot program and full and instantaneous awareness of the flight conditions and the surrounding environment. Generally, TOAF maneuvers include considering three issues simultaneously. First one, trajectory, trajectory generation with terrain and obstacle avoidance purposes and satisfying mission effectiveness and safety. Trajectory tracking via designing an effective controller and sensors data fusion for terrain data update and navigation purposes. The main issue pertaining to TOAF maneuvers is optimal trajectory generation. As mentioned earlier, in lower altitude flight, it is desirable to find a safe trajectory that is compatible with the flying vehicle's dynamic capabilities and at the same time optimizes certain operational factors including time, fuel consumption, control effort, vertical acceleration, and so forth. Separating the flight dynamics of the vehicle's motion into distinct longitudinal and lateral channels reduces the computational complexity of the path planning. Many researchers prefer using simple dynamic models rather than a complex one. With the same reasoning, in this work, we use the longitudinal dynamic of the flying vehicle as a mathematical model proposed by many researchers in TOAF path planning, and these are summarized in table 1. Previous work in low altitude flight referenced trajectory planning have focused on considering the dynamic feasibility of the path by selecting an approximate algorithm. In some of the approaches, the paths are generated with the assumption that the obstacles and terrain profile have already been specified, such as the works proposed in some TF by TA trajectory planning approaches. The three-dimensional or two-dimensional mathematical models of terrain profiles were incorporated in the motion dynamics, assuming that the profile is twice differentiable. In the works presented, terrain mathematical models were incorporated in the non-linear programming solution algorithm as inequality path constraints. The concept of waypoints and geometric methods of path planning has the advantage of low computational time and complexity and the ability of online implementation. However, in geometric path generation approaches, aircraft dynamic limitations are considered by limiting neither maximum normal acceleration or load factor, which is only limits the path curvature. Therefore, it would be the task of the control system to match and track the reference trajectory. Furthermore, these methods do not guarantee optimal and dynamical feasibility. Yeah, here showing the table aircraft trajectory planning approaches. In the left side, trajectory planning approaches and description and related research works. Assuming the flat earth model as an inertial frame of reference, standard atmosphere, and regarding the aircraft as a point with constant mass during maneuvers, the aircraft longitude equation of motion is the parameters x, y, v, and rho are the problem state variables respectively, explaining the horizontal range, altitude, velocity, and flight path angle of the aircraft, and g is the gravity, acceleration. The term L and D are aerodynamic lift and drag forces, which are computed as follows: L is equal to 1 by rho v square SCL. This is called lift equation. We know that the lift is defined as lift is a force that is perpendicular to the relative velocity. Relative speed. And drag is parallel to the relative velocity. When the L by D ratios are maximum, then less fuel consumption occurs. The other important aircraft performance parameter in TOAF maneuvers is the maximum flight climb rate. The performance parameters taken into account as an equality constant according to 9, where ROM, CM, max, white boring, SOM concept. Conformal mapping is a mathematical method for transforming the solution space of a mathematical problem into another solution space presented in the mathematics of complex numbers. A complex function w is equal to f of z, where z is equal to x plus yi and w is equal to u plus vi are complex numbers, is conformal in a specified domain if and only if is non-zero over the entire domain. Conformal mapping preserves the angle locally between two differentials. The other important property of a conformal map is the existence of a local inverse. If f of z is implicate z of and the derivative of the function. Conclusion. In this presentation, a simplified virtual model of obstacles is generated via the concept of conformal mapping using the Schwarzschild-Christoffel theorem. The trajectory planning process does not demand exact information of the obstacle or terrain. The trajectories were generated for multiple SOMs for the minimum time, height, and vertical acceleration, and a composite TF performance index. To obtain more feasible solutions, the aircraft maximum ROC and ROD are also considered as an equivalent constant in the direct geospectral algorithm. It is observed that for hypothetical scenarios, the aircraft flies near the SOM with low elevations, whereas in the time optimal cases, the aircraft flies a straight shot path with the maximum speed to destination. In the minimum vertical acceleration scenario, the aircraft selects a long duration path with the minimum use of the total. The results show the effectiveness of the proposed approach in simplifying the effect of barriers in the low altitude route design process, which could be inferred as a novel framework for using of unconstrained trajectory planning algorithms in constrained problems. Thank you for watching.